mass consisted of atoms, or whether it was just some continuous jello that you could just keep chopping apart into smaller pieces forever, including a gas. There's no reason why that couldn't have been the case, hypothetically. And it wasn't until the 20th century that we sort of found that in complete resolution to that. But it was Boltzmann, I think I mentioned this previously, in his interpretation of the ideal gas law in terms of kinetic energy. And this, well, I've erased it now, this KT, 1/2 KT energy postulate for any given particle in any given movement. That was the start of an acceptance of the atomic theory of matter. So, I mean, you think about it in a historical sense, it's pretty cool. I mean, it's, somebody created a boat, now we can start extending beyond land masses and looking around. That starts somewhere, so it's a pretty cool direction. So let's put all of this stuff into practice, and we're going to do this in the context of using gas systems, closed gas systems. What does a closed system mean, by the way?
Constant volume?
No. A closed system in its least precise but most inferred definition is a system of constant mass. In other words, you have 25 particles, you have 100 particles, you have some system of matter, right? There's your, right, you always define your system by some, mass, mg or whatever, and you use, there's your free body diagram. Well, that's, your closed system is just what you distinguish and isolate from everything else. And if you can isolate that system and close it off, then we can look at what the consequences are of heat transfer on that system without worrying about all the other complications of losing 3 and gaining 4 and all of these other things. So everything we're going to apply then comes down to gas systems and closed systems, or gas matter in closed systems. So you already talked about the thermodynamic processes, so I'm going to put it together and talk in terms of cyclical processes. A cyclical process is a process where from beginning to end, you end up exactly where you started. Now by exact, I mean pressure, volume, temperature, assuming the same number of gas particles, or the same number of particles. So, really, it's closed system thermodynamics. So, closed system cyclic or cyclical processes. Now, we've got 4 processes that we're going to use and apply in various ways and just kind of see what the natural consequences of them might be. Now, to this end, again, the closed system means that from start to end of whatever the process or chain of processes are, you always get back to the beginning. So the initial state of the system is the same as the final. And just to hypothetically draw it out, I'm going to use a pressure volume graph. Did he do pressure volume graphs at least to talk about isothermic processes and?
Yeah, he used your
overheads.
Overheads, yeah.
So let's look at a pressure volume graph. And by the way, what might be an advantage in general of using a pressure volume graph? Hopefully he mentioned something about
You can see the area under the curve. You've got, if you have work.
For any representable graphical curve, the area bounded by the x-axis and that curve is the work associated with that process. So that's kind of cool. That's why pressure volume interpretations are kind of nice. So a closed system, well, if I took a system and I start right here, I'll call this state 1. If I go, say, over to here, to some state. And I'm going to draw a little arrow to indicate the direction. Well, certainly, then, just as what we talked about, the area under here would in fact do the work. Right? Basically, you're integrating PVV. That's the definition of the area under pressure volume graph. Is this a closed process?
No,
Why not?
or it's not a cyclical process. I don't know.
Well,
I mean,
I'm
because
sorry,
the
I meant
volume
cyclical. I said
changes.
closed, it's closed system, but it's not a cyclical process because I've ended up over here. Now, what type of a process is this, by the way? Or at least most likely, let's say most likely.
Isobaric.
Isothermal.
Isothermic, isobaric, well, what's the easiest way of knowing? Does the pressure change?
No, the volume.
So if I've got some pressure here in one atmosphere, 100,000, and I just stay along the horizontal, it's isobaric. Doesn't matter, right? Which means, first of all, I know the volume changes, but it also means fundamentally the temperature changes. It has to change. Because if it were isothermic, or if the temperature didn't change during this process, how do you get a volume to be larger and keep the temperature, or keep the pressure the same? You got to warm it up so that as it occupies more space, the particles, which are now less dense, have to still pound against the walls of their container in the same manner they would have done before, but now it's happening with fewer occurrence because they're all spaced out. So the only way that can happen is if they're transferring more energy every particular time they hit, which would imply that they would need to be moving faster in order to cover that space, and that each momentum transfer is higher, which would imply that the only way to get a constant pressure and a higher volume is to heat it up. So it's an isobaric process. Now, if I were then to do something else, whatever, as long as I get back there, there's my closed process. Or I'm sorry, it's a cyclical process. This is ridiculous, but if I had undergone some series of maybe, this is almost constant volume, maybe call it isochoric. Other than this little rounding, I don't know, maybe whatever is going on there. But by the time all of this happens, if I get all the way back here, when I'm done, so that this system can repeat, cycle again, one complete occurrence, it's a closed system. It's a cyclical process.
Now you have a network enclosed inside of the.
Yeah, and the area enclosed inside, no longer bound because it's a closed graph. The area inside here is certainly the network associated with that process. What else is also happening? We know something. Temperature has to be changing, at least at some points along the way, which means internal energy changes. The work here is not the same as the total work in each of these individual phases, because you're going forward, you're going backward, you've got all kinds of stuff going on here. There's a heat exchange. There's heat that's flowing in or out of the system. Otherwise, you cannot have all of these negative pressure volume possibilities without a corresponding temperature change to balance these and ultimately satisfy the ideal gas law, which is the same and always consistent for every state along the way. So don't forget, everything has to obey this basic relationship. You take the product of all this stuff, it always equals this constant 1.38 times 10 to the negative 23rd joules per Kelvin. Okay. Now, if you look at it this way, the net area is this stuff, right? But here's something that's counterintuitive. it's going from the top part, if we just look at the top part from here to here, it's going from right to left, which implies that the integral under the pressure volume, if we were to calculate the PDV integral over from here to here, that's going to be negative. And that area bounded by this axis is going to be a lot larger than the positive area of going from here to here, all the positive forward movement. So in this particular case, the net work is actually a negative number. This is significant. We think of it as a positive, but it's negative because the higher side is always going in the negative direction. What's a negative area? Well, a negative area doesn't mean anything in reality, but a negative area mathematically is certainly achievable. It's a negative integral. It's a negative value. This means that the system doesn't do work. There's net work performed on it. And here's a good rule of thumb. Any counterclockwise cyclic process has a less than zero network. In other words, you have to do work to the system to get it to do something. So it's absorbing work, or work is being performed on it. This is important. There's a name for this type of system. This is a refrigeration system. We'll come back to that in a second, but this is what's called a refrigeration cycle. Firstly, we had a process that we could undertake that goes in the opposite direction. And we'll make this one a little bit easier to see, and we'll deal with it. So say we started here, but instead of going somehow like this, what if we started here and maybe we went up here, thermodynamic process. And let's just even make this now tangible. So let's assume that we have n equals, now we got to use all these horrible numbers, but how about 3.5 times 10 to the 24th particles? And let's assume that it's a diatomic gas. The reason a diatomic gas is that more often than not, any gas system primarily it's most likely going to have air, nitrogen, or carbon dioxide. If it doesn't, it's just more expensive. Helium, argon, you'd have to use a gas that were monatomic. So we go from some point here, and I'll put numbers in here now so we can say something about it. So we've got this many particles, and we start out at some condition. How about 0.01 meters cubed? Got to use SI units for meters, for volume. You don't want to use, if you want to calculate Newton quantities, joule quantities, you need SI units of volume. So meters cubed, not liters or centimeters. And then the state undergoes maybe a process like this. To a new volume, and maybe let's make that volume how about 0.03. Better give a pressure too. Well, let's start at 1.5 times 10 to the 5th Pascal. 150,000. I'm writing small here because I accidentally looked it up. And this system goes up to, say, 4 times 10 to the 5th Pascal. Gotta know numbers, so I just put numbers in there so we can deal with it. We then reduce the pressure so that we come back to the same original pressure, staying alive. When in doubt, just cheat your diagram. Call this state 4. So basically, we're at some volume, we lower the pressure. Then, ultimately, at that pressure then, we collapse the volume. So we end up where we start. Cyclical process. This is a clockwise. Why did I see that backwards? I meant counterclockwise. I'm thinking one thing, I'm writing something else. This process is counterclockwise. I didn't mean to write clockwise. I'm writing and trying to do too much at once. This process, if you just look at it on the surface, the forward pressure-volume relationship is larger than the backward pressure-volume relationship with no work associated with the sides. This means there's more positive work, if you go from 2 to 3, than there is work done on the system as you go from 4 to 1. So in this case, the net work, which again is the area in this curve, it's a positive value. So in this particular system, the system performs net work. Now, if this system is undergoing this type of a process, if it does work, that makes it ideal to be used in a practical sense for something. This could be an automobile. This could be some process where whatever it is that this thing does, you get work out of it. Right? That's sort of the ultimate goal in industrial technology, is to get work out of it. Now, where does the energy come from? Speed. By hook or by crook, one way or the other, there's heat energy absorbed. Has to be. Can't do work for nothing. And if you end up where you start, there has to be some other energy to account for that work, and you end up exactly where you start. Right? All kinds of little subtleties. This is called a heat engine. Okay, so anytime you see a clockwise process, that's a heat engine, that's a system that does work. Anytime you see a counterclockwise process, that's a system that requires work in order to undergo its process. And usually that involves absorbing energy from something else.
So then the first line is counterclockwise equals negative network?
Yes. Okay. So it's work performed, I'm leaving out words as I'm trying to write fast. It's performed on the system. But the W that we talk about, a pressure volume, an expansion of something, we're looking at the work something does on its environment, not the work the environment's doing on it. So it's exactly backwards from body diagrams and Newton's second law from chapter 1. Okay? But it's the practical side. It's not the outcome, it's how you achieve the outcome. Okay, so real quick, how much work involved in this process? How much work is gained? What's the mechanical output of this system?
2.5 times 10 to the 5th times 0.02.
The way you always calculate the work, if it's a rectangle, this is a rectangle. Then you just calculate the area, right? The width times height. Always calculate it that way. So if it's not, then you got to integrate the phases. But if you can do it this way, life is good. So for an easy example, such as this,
5,000 joules.
To get the net work, it's the area under that curve. No work on these sides. All the work is whatever mechanical output occurs here, and then you subtract the work performed on the system to get back to where you started. So the net work in this particular case would be the work as you go from 1 to 2, plus the work associated from going from 2 to 3 in these phases, plus the work to go from 3 to 4, plus the work required to go from that fourth state back to the beginning. And 2 of these states are 0. So to calculate the work then, in a very systematic way, what we would do is we would calculate the work done by evaluating the integral from 2 to 3. Which would basically be, in this case, the pressure, this high pressure, I'll say pressure at 2 and 3. It's the same value, so it's a constant in this particular case. The high pressure. We all call it the high pressure. And multiply that by delta V. And I add that to this. And then to calculate the work to get back home, I take the low pressure and multiply that by delta V. I'm doing it this way just to kind of reduce the problem so that you can see it. In the end, because it's a rectangle, what we're basically left with is P high minus P low. I've got the minus sign here. So it's times delta V as a magnitude value. Or maybe I'll even say it this way. I won't say delta V, I'll say V high minus V low. In other words, it's the height times the width. So it's, to that end, it's about 2.5 times 10 to the 5th newtons per meter squared, Pascal, and a volume difference of 0.02 meters cubed. Some of the meter units go away. We're left with newtons times meters. That's a good thing. It's going to be in units of joules. And ultimately, then, it's going to be about 5 times 10 to the 3rd. Yep. Or 5,000. Not bad. So whatever's going on, you're getting 5,000 joules of output work. That's good. Now, the question is, though, how much energy was required to do this, for this process to happen? What's the rest of it? Here's what we know about any of these thermodynamic heat-type systems. Okay? Whenever you have a heat engine, and I'm throwing lots of stuff in different ways at once as we approach this, you need to. For any heat process, this is always true in a general sense, for heat engines. Ultimately, we're getting work output, right? We're getting some net work, which requires, a little arrow here, that you're getting work output, but you start where you ended. That means you're at the same temperature, but somehow you got mechanical work without changing temperature. That energy has to come from somewhere else. It's come from the outside. The requirement is you have some heat flowing in. Now, in a perfect world, all the energy that you burn in gasoline would go right to moving the automobile. Life would be good. And we'd never have to worry about energy conservation because we'd always have the same amount all the time. Right? We'd always have gasoline because it'd never change. We know that doesn't happen. Why? Part of the reason heat only flows one way. No matter what, as you heat your engine, you lose your engine temperature block rises and it cools off to the air, so you're all losing something. That's not energy you can use anymore. So somewhere along the way in this process, and it's going this way, you also have some energy that's not accounted for. Right? And we can make the presumption ahead of time that energy in does not equal the energy out. The work output. Can't. We're always going to lose something. So I'm just going to indicate over here that there's going to have to be a certain amount of energy loss. Now this is cyclical, so it's not so much looking at a thermodynamic process on an individual step and applying the first law. This is saying over this entire event, somewhere I've absorbed energy, somewhere I've lost energy. The difference between the energy I use, or the energy I gain, that I absorb, and the energy that just gets wasted, that's going to be what ends up doing mechanical output over. In other words, for this type of a process, we use a certain amount of energy. But the net result of that energy is that we get a certain amount of output, but we also have to release a certain amount of just lost heat. Okay? That's the heat of the exhaust, the gas that comes out the back of your automobile. That's the heat of the engine block and the energy that's being radiated when you're running the coolant and all of that. So, you burn some amount of gasoline, you get 5,000 joules. How efficient is it? What's the relationship of work to energy requirement to do it?
Less.
It's going to be less. Let's calculate the efficiency. In order to get the efficiency, we need to figure out how much energy is being absorbed and how much is being lost, all of these things along the way. So let's look at, then, how much energy gained by the first law of thermodynamics. What's the energy absorbed in each of these steps? What is Q? Not necessarily absorbed, sometimes it's released. But bottom line, for each of these processes, we could say something. If you stay at constant volume and increased pressure, you know what you call that type of a phenomenon?
Isochoric.
It's a pressure cooker. Yes, it's isochoric. It's a pressure cooker. All right? You've got a locked up system and you put it on the stove and it just gets hotter, and as it gets hotter, the pressure rises, and that's an isochoric process. In order for the pressure to rise, it requires the temperature rise, which requires that energy be absorbed. So somewhere along the way in this process, we have Q flowing in. May not be all of it, but there's Q that's flowing into this system. No work is being done, but the temperature's rising. If the temperature's rising and there's no work output, what does that say about the internal energy change?
Equals Q.
Internal energy change equals Q. So if I want to know how much heat is flowing in this first part, how would I do it? I'm going to erase this. Write out the first law of thermodynamics. Write it out on paper. Write it down. Always start there. Look at your assumption. So you could write it out as dq, but since we're looking at a non-finite, at a finite, not infinitesimal process, in this particular case, we can say that Q is going to be equal to the change in internal energy plus the work by the system. This is 0, which requires then that Q, and by the way, this is step from 1 to 2. Got to do this 4 times. Q from 1 to 2 then, it's going to be, how do we calculate internal energy change? Well, if it's a diatomic gas, then I know I'm going to take the number of particles times 5 halves, K delta T. So, how might I solve this problem?
Well, you have N, and you know both be constant.
You know P and V, so calculate T and then solve for delta T? Maybe?
You can use PV equals, I guess not nRT, you use NKT.
NKT. Let's make our life easier. To solve this problem, we got 2 choices. And by the way, this delta T is the temperature change as we go from 1 to 2, right? So, hypothetical, I'm not going to write this down. The intuitive direct approach is to say, I know N, I know P, I know V, I know K, solve for the temperature here, solve for the temperature here. Solve the problem. There's an easy one. These are the things in the short time I want you to know. If PV equals NKT, this implies that P over T is related to N over V times K. This is the Boltzmann constant again. Is that reasonable? In other words, no matter what, for this type of a process, volume and the number of particles doesn't change. This is all a constant. However, if I change P, the only way this expression remains a constant is if there's a corresponding temperature change simultaneously. Is that reasonable? This is the art of using the ideal gases.
Recognizing when things are constant.
Yes. Yes. Because of this, watch what we can do. In other words, if I solve for delta T is going to be related to delta P times V, and I'm leaving it, there's my N, okay. It's N over KV. Only two things can change, and they have to change pairwise, proportionally. The pressure changes, the temperature will change in a relative proportion. And the way the quantity of the temperature and how it changes is related to the change in pressure times volume times N, okay, divided by N, okay. So I don't necessarily have to solve all of this in a crazy, crazy sort of way. I might just say, I've got N, I've got 5 halves, and now I've got K times, oh look, I might as well write my K with the conversion in it. Don't even need to worry about it. Bring that over too. Right? Just mathematically simplifying. K times delta T is another way of saying delta P times V divided by N. Look at what happens to the N's. I've got an N in the numerator, N in the denominator. So if I want to solve the problem, all I have to do is take 5 halves of the volume, there's your constant, times the change in the pressure. And this is how you calculate the heat absorbed from the pressure change in an isochoric process. This is Q, from 1 to 2. Pressure is positive, Q is positive. That means heat's flowing in. Volume, the pressure change at a particular volume, and then this is how all that information gets spread out, right? 5 halves because you've got all these different ways this thing can move. Rotate, move forward, backwards, up, down, left, right. But when I calculate it, just make my life easy. 5 halves times with a volume of 0.01 times a pressure difference of 2.5 times 10 to the 5th. I'll just write it Pascal. For your own notes, this is for an isochoric process. You don't necessarily have to remember all of these because it just sort of comes organically, but just to the extent until these things become more intuitive. You can always do it this way and work as 0. So, give me a number for that.
6,250 joules.
So think about what we've got. I'm going to make a little table for state. Maybe I should put it.
We're already more than our output.
Yeah, we're already got Houston. We got problems. Got work, and we've got Q. Well, as we go from 1 to 2, there's your isochoric. There's no work, but even before we get started, just to get the ball rolling, we have to absorb 6,250 joules just to get hot enough to get to a certain pressure in order to get some positive work done. You got to have your coffee before you start taking the exam. Get revved up and roll. Sure. Okay, so now you can see the intrinsic limitations of energy. You can't just throw it in and get it back out in a good way. So we had to heat it up. Okay. Don't forget this, though. That's why I support. Let's add it to the next step. So how much energy is absorbed as we go from here to here? Now what happens to the, we know there's positive work done. What happens to the temperature also? Does it stay the same? Why not? If this were an isothermal process, isothermic, what would the curve look like? It look like that, right? Pardon me, I have a little boil in my throat or something. It would look like this. The fact that it doesn't, and the whole curve is up here, instead of the temperature being down here, means it also gets hotter going here. So even when the work is done, you're absorbing more energy than you're getting work, because you got to heat the damn thing up more just to get it to expand. Crazy, crazy. So, to calculate Q,
So how do you catch
as
up?
we go from 2 to 3, we got two things to deal with. We got to deal with the change in the internal energy and the work as we go from 2 to 3. Just got to do it. So, is there any way we can do anything with this? Yes.
Well,
You're
the
absolutely.
word is P delta V.
So first of all, we have P delta V, right? As we go from 2 to 3. That part we're good? I'm going to change colors here because this pen is just jumping on me. But the internal energy change is going to be 5 halves N K delta T. As we go from 2 to 3. Wait a second. If we play that same little game where we keep pressure constant, if volume is the only thing changing, then temperature is going to rise with volume rise as well. Again, I can calculate the temperature using the ideal gas law. Since I know all this stuff, I can go all the way around. But I don't have to. I can just as easily say that Q is going to be 5 halves NKT, which is another way of saying P delta V. And I'm going to add that to P delta V. This is just 7 halves P delta V. Well, I think you can maybe appreciate if this is the work, you're absorbing an additional 2.5 times the energy for the work being done. So for every 1 part of work, you have to add another. You have to add another 2.5 parts of energy. That kind of sucks, but it is what it is. So tell me what that calculation does for us. On the one thing, since I already knew what 5 halves PV is, I can actually probably get this without having to do too much extra effort. Right? I'm just adding how much more energy am I adding? I'm adding 1 into 3/5, so we did the calculation, we used the numbers. I know estimates are not always the best way to solve a problem from your side of things, so we'll just say it's 4 times 10 to the 5th. There's our constant, and we have volume change of 0.02. So it's going to be 8 times 10 to the third, and we got 7 halves of that.
28,000.
Yeah, that's what I'm getting. 28,000.
Nice.
That's for production.
Okay, that's
The
Q.
work is, the work is 8,000 of that.
And this, the work, is about 8,000. This is just P times V. I didn't calculate because we sort of shortcutted it. But if I wanted to include that, you get 8,000 out of that first step, or that second step of work. But you end up having to use this much energy to do it. So this is from 2 to 3. Now all is not lost because some of the, I don't know, we've got other things going on here. Actually, all probably is lost. Think about this for a second. The inference of this is just to get 8,000 joules of work. And by the way, we're nowhere close to 8,000 joules, right? How much we said that we actually did, how much work? 3,000? 5,000?
So we're gonna lose 3,000.
We're going to lose 3,000 joules of that. So it kind of sucks. So for all this energy absorbed, I'm going to get less than this amount of work. And this amount of work is just assuming I don't have to do work on the system to get back to where I started. So this is like the highest of it, and I'm going to lose some of this. Oh, God. Kind of pissed. So very quickly, if we go from state 3 to state 4, again, I know that there's no associated work with that stage. And the heat, then, again, we'll play the same game. And the heat to go from 3 to 4 Q from 3 to 4, since it's a isochoric, is going to look like 5 halves V delta P as we go from 3 to 4. So delta P is a negative, but the same value, but just a negative quantity. And V is now a larger value rather than a smaller value. So it's going to be about 3 times higher than it was. It's going to be about 3 times higher than this.
Negative 18,750.
That's the energy that's coming out. I'll put a minus sign there because this is out. These are positive, these are in.
Why is it gonna be 3 times higher?
Because I'm doing the same compression at a higher volume. And by the way, I should have probably put this in here. Q is also flowing in here, has to. We just think in terms of our diagram. Temperature's rising and positive work. So positive increase in internal energy and work being performed. So Q is flowing in. And now we can see, ooh, one thing, well, not good, but we're also losing Q here. Lost like 18,000 of it. Now we just got to get back home. And to get back home, do the work. Well, maybe we don't. It's P times delta V.
1.5.
So it's about 3,000. We do 3,000 joules of work, but it's negative now because the delta V is negative. I'm going from 0.03 to 0.01, so that's a volume difference of negative 0.02. Heat loss? Okay, I'll take that on face value now, that it looks reasonable. No, does that look reasonable? We'll see. Yeah, it does. We look at the net for the process. We might see that Q, or I'm sorry, work is 5,000. And all of this stuff, this would be Q out. We add all of this up, we're gonna get, I don't know, what is that number? Take 6,250 plus this, calculate this. This is Q out. This is network.
It's 5,000.
Is this 5,000?
That's what I'm getting.
Oh, maybe I've got that backwards then. This is Q in minus Q out. No, I'm sorry. This is not Q out. This would be Q in minus Q out. 5,000. These need to be equal. Your balance ledger needs to be equal. I'm sorry. So I'm going to run up to the restroom. I know you guys got to get ready to go, but it's our last day of our class. I don't have tomorrow. So what I'd like you to do briefly before you go is calculate the work divided by the energy absorbed. That's the efficiency of this system. In other words, that's not the economy, but it's the energy output relative to the energy needed to produce it.
So take all the Q's in absolute value?
No, only the Q going in, because the Q going out is just released. That's heating up the muffler and the tailpipe and everything else.
Alright, it's just 34,250.
Let's just do.